Good morning or good afternoon. Thank you for joining the SimScale demo and discussion session on LED thermal management. We'll make a start on this session. If you've got any questions as we're going through, please feel free to ask your questions using the questions functionality in GoToWebinar. That should be down the bottom right-hand side of your screen. So first of all, I'll introduce myself. Hi, I'm Steve Lene. I'm an application engineering manager at SimScale, and I'm going to be your host today. I'm going to give you an introduction to SimScale, and then the star of the show, David Short, will be doing the presentation. David's one of our senior application engineers here at SimScale, and he brings with him a marine engineering background, as well as experience working within the CAE world. So let's make a start. Who are we? Well, SimScale is a Munich-based company. We were founded in 2012, and we've got a global presence. There's millions of jobs being conducted worldwide, simulation jobs that is, and we're funded, so we're going to be here to stay. What do we do? Well, at SimScale, we created the world's first cloud-based engineering simulation platform. You can use this platform to do fluid dynamics, CFD, solid mechanics, FEA, and thermodynamics. And all of this is accessible just through a web browser using the cloud-hosted capabilities that we enable. There's thousands of brands that trust us and use SimScale for their simulations worldwide. On the screen here, you can see a selection of some of the brands that use SimScale. How do they use SimScale? Well, they use SimScale to accelerate their design process, to simulate earlier in the design process, to test performance, optimize durability, and improve the design efficiency in their organizations, all while using cloud-based simulation software. So, how does this compare to traditional simulation? Well, with traditional CAE, there's typically high fixed costs, and that's associated to the specialist hardware that's required to be installed and maintained, and the specialist software that must be installed and maintained locally on that hardware. Traditional CAE tools are built for specialists, and this means that there's specialist training and extensive experience required to get the most out of the software. Typically, computation time is measured in days or weeks, and it's difficult to parallelize processes because the hardware and software is occupied during a simulation. So, how does this compare to the benefits of what we offer with SimScale? Well, with SimScale, there's no upfront investment. There's no installation or maintenance of hardware or software, and it's extremely easy to set up. All you need to do to start simulating is log in to our website, create an account, and you can start. We enable seamless collaboration within your organization, and we provide world-class support. In the software, you can ask questions directly to our experts to help you with your simulations. Computing time is also typically measured in minutes rather than weeks. And because we're leveraging the capabilities of cloud-hosted solutions, you can parallelize your processes and run as many simulations in parallel as you like. Okay, so we're now going to hear from David. Please be patient for a moment. David can't join us today, so there might be a minute while the video loads.
Hello and welcome to this SimScale demonstration. My name is David and I'm going to be taking you through an electronics cooling application on the SimScale platform. Specifically, we're going to be looking at a passively cooled LED module using conjugate heat transfer analysis to optimize the heatsink design. So here's a little rundown of the project details for this CHT application. We're going to be looking at a LED module with 7 LED diodes or chips totaling 7 watts of dissipated heat. Okay, and the objective is, as I said earlier, to optimize the design of the heatsink, ensuring the best quality lighting performance as well as the LED lifetime. And really the result of interest that's going to indicate both of these two parameters is the junction temperature of the LED. So that's really going to be our result that we're going to get to as our result of interest. So the simulation, the analysis type that we're going to be using is a conjugate heat transfer simulation. So this is a coupling of your flow physics, so based on finite volume method CFD, coupled with heat transfer capabilities as well. So that gives us the ability to look at conduction within the solids, convection within the fluid air in this case, and also radiation between the solid surfaces as well. Now we're going to be running a steady state simulation and using laminar flow rather than employing a turbulence model. And as I said earlier, the result of interest is really going to be the LED junction temperature, as well as a general understanding of the convectional flow field as well. So here is the CAD model that we're going to be using, or one of the design variations that we're going to be looking at. As you can see, it's a finned heatsink with 7 diodes placed within the bulb. We want to compare a number of different heatsink designs to understand what gives the best cooling capabilities, and then as a secondary piece of information will be actually the amount of material required, because obviously that's going to have a bearing on the cost of manufacturing as well. So these are the 3 different designs that we can have a look at, and what I'd now like to do is jump into the SimScale platform, so that I can show you both the results of a single design, and then we'll set off a simulation together for the next proposed design. So here we are in the SimScale platform. We're firstly having a look at the results to our proposed design 1, where we can see the heatsink on the outside here. And you'll notice that we're running a quarter model, so we're taking advantage of the symmetry of the model, so that then we can really optimize the run times of our simulations. So there's no need to run the full model if it's symmetrical. So here is the heatsink. We can see the temperature distribution across the heatsink. You'll notice here on the bottom that we've got the temperature actually plotted on the solids, and then in the fluid region on this cutting plane we have the velocity magnitude as well. Additionally, I've put a few particle traces actually within the bulb itself, so that we can see what's happening in terms of the natural convection within this small air volume as well. Our result of interest is really the junction temperatures, and we can find these junction temperatures. If we zoom in on the diodes themselves, we can pick points within the model to inspect temperatures, for example. So we're looking at the temperature of 77.25 degrees Celsius on the case surface of the LED. So that's not going to be the exact junction temperature. You'd want to then back calculate the junction temperature using the thermal resistances provided by the manufacturer to get from your case temperature back to the junction temperature. So now what I'd like to do is show you how to set up a simulation like this, and for that purpose we're going to set off a new simulation for the next design candidate. So we can go over here to our simulation tree and duplicate the simulation we've already done and simply apply it to the next geometry. Okay, so if we go to geometry here, we can then select from the geometry list from the geometry tree, any of the CAD models that we've loaded into the SimScale platform. So let's go for our version 2, the design 2, and then we can set off this next simulation. So as you can see, it's loaded into the viewer. And we can see that we've got some bulkier heatsink fins with a larger spacing as well. So when I started off that, when we assigned the new geometry, what it firstly did is automatically found the interfaces. So the interfaces between both the solid parts and also between the solid and the fluid regions as well. Okay, so that's done automatically for you, and we just need to worry about the actual design parameters, and what we're going to do is then go through and assign these design parameters, so that being the materials and then the boundary conditions, which is dictating the physics of simulation. So our carrier fluid is going to be air, so we can apply that both to the external air volume as well as the internal bulb volume as well. So then we've got our air. So now let's assign the solid materials as well. So we're modeling the diodes themselves as silicon capped LEDs. We're modeling the heatsink as anodized aluminium. The PCB board is a metal core, so an insulated metal substrate board. And the wire is a copper wire. We've got a ceramic substrate as well, and then a polycarbonate screen. Now, in terms of the physics, the boundary conditions for this simulation, we're going to be running this as natural convection inlets outlets. So that allows the air to enter and escape through these surfaces. So we're modeling the LED suspended in a large volume of air. So the additional physics that we need to add is adding the dissipated power to the LEDs themselves. So for the full LED, the one that isn't cut by the symmetry planes, we're applying 1 watt, and then we've got our half LED 0.5 watts and the quarter 0.25 watts as well. Then it is time to set off the simulation. So we can leave the rest of the simulation control up to default. So meshing and simulation control, we can leave up to defaults in a simple simulation like this. So we get an estimation of the time it's going to take for the simulation, as well as the amount of compute resources it's going to use. So if we're happy with that, then we can start the simulation. So now that's up and running in the cloud. We're not going to wait for the results here. I would like to show you the results as a comparison between all 3 designs, so that you can get an idea of the sort of design feedback that you can get out of SimScale simulations. So let's jump back into the PowerPoint. So here we can see a side-by-side comparison of the temperature distribution for each of the 3 designs. And we can clearly see that the original design is really not optimized for the flow situation. So it's not doing a great job at cooling these LEDs. Whereas design 2, we have a nice low and uniform temperature distribution across the heat sink, the aluminium heat sink. And we can actually understand why this is the case as well by looking at the convective behavior. So if we look at the original design here, we can see that there's actually not that much penetration of the airflow to the center of the heat sink channels, whereas in the proposed design 2 we have a much greater amount of flow within the heat sink channels, thus increasing the cooling capacity. And if we look at the junction temperatures themselves, or the temperatures on the diodes, then we can clearly see the benefits of the proposed design 2 in terms of the heat sink performance. So both in terms of cooling capacity, which is going to ensure the good lighting performance as well as long lifetime, and also we're going to be having gains in terms of reducing material costs using proposed design 2. So that was a quick introduction into the electronics cooling capabilities of SimScale applied to an LED application. And we can really see how SimScale allows designers and engineers to gain design feedback from running multiple simulations using cloud resources. Thank you very much for watching.
That was excellent. Thanks to David for that. Unfortunately, David can't be here to answer questions live, but we do have Darren on the line to answer questions. So if you've got any further questions to send in, please don't hesitate to use the questions functionality in GoToWebinar, and we'd be happy to answer your questions. We've had a couple come in that I'll get onto in a moment. Okay, Darren, so one question we've had come in is how much project data can be stored in SimScale?
Oh, very good question. So project data isn't actually restricted in terms of how many results you can store on SimScale, etc. Actually, the only thing you're restricted to is to how much compute resources you're allowed to use. So you might have a set amount of core hours for your account. Once that's used up, you've got to purchase some more or be sponsored somehow. But in terms of actually storing that data on our platform, there's no actual limit. I think
Great,
you're
thanks.
muted. Oh, okay, cool.
Okay, another question we've had is what CAD formats can be read into SimScale?
Ooh, another good question. SimScale actually supports quite a variety of different CAD formats, so ranging almost across many different industries where the typical CAD formats might be Parasolids, it might be SolidWorks, CATIA files, all of those supported, but also the more generic ones. So STL files, step files are also supported. And then moving across industry, maybe to the AEC industry, Revit files and Rhino files are additionally supported. So really, if you've got a CAD 3D software, then we're probably going to be able to either support it directly or indirectly.
Great, thanks, Darren. So another question that has just come in is how can the results be downloaded? Is it possible to post-process them locally?
Yes, absolutely. So although we have, of course, got the online post-processing capabilities, it's important to note that you can actually upload and download a lot of different data in different formats. So typically this type of simulation, you can download its entire results set as an open source file type, which can then be opened in PowerView and converted to almost anything you like in terms of CSV files, text files, etc. So yes, you can transport your results to almost any external system.
Great, thanks, Darren. There's a question here that I'll take about, is this going to be recorded? Yes, this session is recorded and it will be sent out to all of the attendees as an upload to YouTube afterwards. So keep an eye out in your inbox for that. Okay, if there's nothing else, I think we'll close it there. So thanks, see you soon.